Okay. All right. So, good morning, everyone. And for those of you who are watching this video at a later time, hello to you too. I do want to start off by saying that friendly reminder that these are just some bonus questions that I want you guys to practice with. But obviously, these few questions don't cover the entirety of everything, right? I've tried to cover a lot of it, most of it, but it doesn't cover everything. All right, remember there were some other things I told you make sure you're really comfortable with. Make sure you're comfortable with real world significance, right? Not just the statistical significance. Make yourself comfortable with generalization to a larger population, right? I think both of those topics were in 6.5, which was right after we had discussed the type 1 error and type 2 error, which is also in 6.5. I do have some examples here with type 1 error and type 2 error, but I didn't include examples of the real world significance. Hey, morning. Of the real world significance and the generalization. Also, make sure you're comfortable with identification, recognizing what values within a problem represent. We do have a couple examples like that today, as well as, you guys make sure you're comfortable with everything. Everything's fair game, like margin of error, z-score stuff, making sure you're understanding it. So yeah. Okay, so these first couple problems are examples in which we are just doing identification, okay? So number one, and actually, wait, that's not even what I want to do it on. I need my good notes. Here we go. Okay, here's my good notes. Number one, in 2008, 30% of pet owners believed that vets charge an unreasonable amount for their services. In 2015, a survey conducted by Gallup reported that 376 pet owners believe that vets charge an unreasonable amount for their services from a random sample of 6,740 pet owners. This is equivalent to about 5.6%. So the only thing I want us to do in question number one is just to identify each of the following values as either the sample size, sample proportion, number of successes, or population mean, okay? So part A, the 30% was here, in which we're told in 2008, 30% of pet owners believe that vets charge an unreasonable amount for their services. So in this case, 30% represents what? The sample size, sample proportion, number of successes, or population mean. I think I heard someone.
Population.
Yeah, exactly. It's the population mean. Back in 2008, they calculated the population mean to be 30%. 30% of all pet owners believe vets charge too much. 376, let's see, 376 is located here. So in 2015, a survey conducted by Gallup reported 376 pet owners believe vets charge an unreasonable amount. So what does that represent?
Number of successes.
Number of successes, good. All right, 6,740, that's a continuation of that sentence. This was from a random sample of 6,740 pet owners.
Sample size.
Sample size, very good. And lastly, 5.6%, and then I said this is equivalent to about 5.6%. So what's that? Mm-hmm. Yep, sample proportion. Very good. That's it. Any questions there?
Could you explain what the population mean is again?
Yeah, so the population mean is the mean of every single pet owner. In this case, every single pet owner in I think, did they say United States? No, it didn't even say United States. So this is just every single pet owner, the mean or average of them who think that the vets charge an unreasonable amount was 30%. And so that was done back in 2008. So we don't know how they went about that, but we can work with that assumption that that is, in fact, the population mean, that's like our starting point.
Okay.
And then from there, basically, usually be like, okay, like, is this still true? Is that population mean still true? Let's do a hypotheses test to see if it needs to be altered.
Okay.
Yeah. Number 2. In a recent election, 52% of all voting women and 67% of all voting men voted for a dog to become mayor of a small town. And that's happened before. Isn't that so cool?
What's a cat? I thought it was.
It's probably been
It's like
both.
a golden retriever. at
Yeah. So which I love. That makes me so happy. So suppose we gather a random sample of 260 women and 195 of them voted for the dog. This is equivalent to about 75%. Suppose we also gathered a random sample of 320 men and 285 of them voted for the dog. This is equivalent to about 89%. Identify each of the following values as the sample size, sample proportion, number of successes, or population mean. And obviously there's more numbers here, so they could be used more than once. Let me go set the timer. I'm going to give you a minute head start.
So you don't want us to specify, are we doing men and women then?
We're not specifying whether it's for population 1 or population 2 or anything like that. Just
No?
in general, is it the sample size or is it a sample size? Is it a population mean? Yeah.
On the exam, is it gonna like, so let's say there's a question like this, is it gonna say like, identify each of the following values as sample size, sample proportion?
That I can't say.
No? Hope it is though. Okay.
And let me actually give y'all just 30 more seconds. All right, I'm going to start going over it. So, and it really doesn't matter what order you do this. And I'm sure some of you guys may have done it out of order. Some of you maybe did it in order. That doesn't matter, just as long as you're able to correctly identify. So 52%, so that was stated right at the beginning. 52% of all voting women. So what was that? What did that represent?
Population mean.
Population mean. Good. I'm going to go ahead and do this out of order. Was there any other population mean provided? Yeah, what was it?
67.
Good, 67% of all voting men. So that's the other population mean. Okay, next 260. 260 is here. Okay, so suppose we gather a random sample of 260 women. What does that represent? Sample size, good. Were we given any other sample size?
320.
Yeah, what was it?
320.
The 320, because we gathered a random sample of 320 men. So that was also a sample size of 320. Let's see, 195. What is the 195?
Number of successes.
Number of successes, because we were told of the 260 women, 195 of them voted for the dog, which is what we're considering to be the success. So 195 is the number of successes. Do we have any other successes?
285.
The 285, because for the men, 285 of them out of the 320 voted for the dog. So 285 is also number of successes. And lastly, or not lastly, but kind of lastly, right over there. So 75%, what is the 75%?
The sample proportion.
Sample proportion, because I said right here, this is equivalent to about 75% right after we would do that calculation. 195 of a 260 women is about 75%, so that's a sample proportion. And do we have any other sample proportions?
Yeah, the 89%.
the 89%, because they went ahead and did that calculation for the men as well. 285 of the 320 is about 89%. So that is also a sample proportion. Good. Any questions so far? All right, let's keep going. Now this page here, this questions 3, 4, and 5 is all just practicing type 1 and type 2 error. And I do want to fix a correction. I had said last week when I said, oh, for sure there's going to be 2 questions about errors. That's actually not the case. There's only one. But I mean, I told you guys there's going to be type errors on it, right? So still got to know it. So let's go ahead and practice it. If we reject the null hypothesis, even though it was true, it really was true, so we probably should have kept it, then what type of error did we make? We made a type 1. Type 1 error. So if you reject the null hypothesis when you shouldn't have, it's a type 1 error. If we do not reject the null hypothesis, also you might see it as if we fail to reject the null hypothesis, even though it was false. So we should have failed it. Then we make a what type of error?
Type 2.
Type 2 error. Okay, so if you reject the null hypothesis when the null was actually correct, it's a type 1 error. If you do not reject the null hypothesis, even though you should have because it was incorrect, that's a type 2 error. So with these following problems, parts A, B, C, and D, I just want us to practice identifying whether a type 1 or type 2 error was made. That's all that's needed, just identifying type 1 or type 2, okay? So part A. Researchers conducted a study on whether the majority of women self-identify as a crazy cat lady. In conclusion, the researchers rejected the null hypothesis and supported the claim that a majority of women self-identify as a crazy cat lady, even though the true population proportion does not support this. What type of error occurred?
Type 1.
Type 1. Type 1. How did we know that?
Because they rejected the null.
Because we rejected it, right? It says, in conclusion, the researchers rejected the null hypothesis, even though the true population proportion does not support this. We rejected it when we shouldn't have. Okay, so anytime you reject the null hypothesis when you shouldn't have, that's a type 1 error. Okay, and in this case, that's what we said right here. The researchers rejected the null hypothesis when we shouldn't have. That's a type 1 error. Part B. Researchers conducted a study on whether the majority of women self-identify as a crazy cat lady. In conclusion, the researchers did not reject the null hypothesis and did not support the claim that a majority of women self-identify as a crazy cat lady, even though the true population proportion is statistically significant. What type of error occurred?
Type 2.
Type 2. And how can we tell?
It did not reject the null. when it
Yeah.
should have.
We did not reject the null. We did not reject the null. That's a type 2 error, even though we should have. Because even though the true population proportion is statistically significant. Remember, if it is statistically significant, then you should reject the null hypothesis. But they didn't do that here. So that was a type 2 error. Okay. I want you guys to try part C and D. I will give y'all 2 minutes. Feel free to talk with your table mate, see if you get the same answers with 2 minutes. I got type 1.
I'm confused about because it says they did not reject the no. Oh wait, never mind.
Yeah.
Never mind. It's type two.
No, it says did not.
And then I type
Just under a minute.
Question. So when determining if it's like a type 1 or type 2, is it just depending on like the first sentence if it's like rejecting it or not rejecting it? Or
I mean, you
That's
want to
what-
read the whole thing is
Yeah,
important,
because, like,
but
some of them-
but the key thing you want to identify is whether or not the null hypothesis was rejected or was it not rejected, and then that will tell you what type of error to be on the lookout for.
Okay. Yeah, because it confused me like on the last like sentence if it would say like, oh well, this turns out to be true or not.
Yeah.
Oh, well, it's kind of hard to tell, but okay.
All right, so let's see how y'all did. So part C, researchers conducted a study on whether more men considered themselves a crazy cat person than women. The researchers did not reject their null hypothesis and did not support the alternative hypothesis. They concluded that the proportion of men who considered themselves a crazy cat person is equal to that of women. In reality, the true population proportion of men who consider themselves a crazy cat person is more than that of women. What type of error occurred? Type 2. Very good. And we could see that here they did not reject the null hypothesis, did not support the alternative. Okay, even though in reality, the true population proportion of men considers them is more than that of women, right? When it's more than that of women, the only way to get to that would be the alternative hypothesis, which means you had to have supported the alternative by rejecting the null. Part D, suppose researchers conducted a survey on whether more families in urban cities or families in rural areas have a pet. The researchers reached a conclusion where they rejected the null hypothesis that the population proportions of families in cities with pets in rural areas with pets are equal. That's what they rejected. They rejected the null hypothesis, which stated that they were equal. Because remember, that makes sense. Our null hypothesis is always an equal sign. They instead supported the claim that the proportion of families in urban cities have more pets than that in rural areas. In actuality, the population proportions in urban cities and rural areas is not statistically significant, which means you should not support the alternative and you should not reject the null hypothesis. But they did reject the null hypothesis. So what type of error occurred?
Type 1.
Type 1. Good. All right, very good. So hopefully this helped a bit with the type 1, type 2 error. Definitely feel free to practice these some more because there will be a question on the exam with regards to type 1, type 2 error. No more than 2, but more likely 1. All right. Okay. Now let's do some practice problems in which we're practicing more like, what's it called? The free response. The free response, right? Okay. So, number 6. Many years ago, Gallup surveyed, that's a typo, Gallup surveyed adult women in the U.S. and asked if they self-identify as a crazy cat lady. In a good way. I do want to preface that. I consider myself a crazy cat lady. So anytime I'm saying this, I mean it in a good way. They found 40% of women did self-identify as such. It is suspected that this percentage has increased in 2023. Gallup gathered a random sample of 1,200 adult U.S. women and found that 504 self-identify as a crazy cat lady. In the following steps, test the claim that at a 10% level of significance, the population proportion of women who self-identify as a crazy cat lady is more than 40%. All right, I want you guys to get a head start on this. How about I give y'all like 5 minutes? Yeah? Okay, 5 minutes. And I'll check in on you then. While you are doing that, if anyone is following on my recording, I'm just going to be downloading the formula sheet. And again, I did make these numbers up, so hopefully they turn out nicely. Hopefully we don't get any 0% like we did last week. I don't think we did. I tried to check, but I checked fairly quickly.
If I don't print, like, if I just did this,
Come on.
is that gonna be a problem? Do I have to have all the, like, this in front of it? and-
Formulas first. I do it and then I write this, like, so on the exam, I would probably do something like this.
I'm
Yeah,
okay
like
either
that.
way. Either way.
Cause you know we know what we're doing, right?
Yeah,
Isn't that
because
the
then,
point?
because then I'll see where you substituted in accordingly.
Okay.
And also, I mean, like it says here, calculate the standard error, so like,
You
this is
obviously,
your, yeah, the standard error.
Right, right.
Yeah.
but I didn't know, cause usually I'm like doing everything.
Yeah, no, like that,
Okay.
like that, those are all fine, okay. I'm almost getting right so that it helps me remember it.
Well, sometimes it's like, what's the P and the P hat and all that. And if it doesn't ask for approximate normality,
Then don't do it.
then don't do it.
Yeah. About 2 more minutes and we'll start going over it.
So when you get answered for standard error, it's like signal, right? Answers equal
Yes,
signal? Okay,
correct.
gotcha.
I should get my steps in. About 1 more minute, and if you don't finish it, that's okay. I know 5 minutes is not enough. I just want to make sure we have enough time together here to finish going over all the questions.
We're going up this, so it's 7.7%, so that's less than our minimum. Good. Mhm. 10. Where's the 10% there? Right here. 10%. Oh, 7%.
No, that was the more than, that was the.
Population.
Yeah.
Mhm.
All right, guys, that's time. Again, it's okay if you didn't finish. I just wanted you to get a head start. So, part A, state the null hypothesis, alternative hypothesis, and state what type of test this is. So, the null hypothesis, or you could denote it as H sub naught, right? That'll be P equals what?
P
What was that? P equals
0.4.
0.4 or 0.40, good. It's your original population mean, or like just your starting foundation, right? Because what we need to compare it to is the alternative hypothesis, which is denoted as H sub A, in which we're told that we want to test the claim that the population proportion of women who self-identify as a crazy cat lady is more than 40%, or so 0.4 or 0.40. Either way. It says left-tailed, right-tailed, or two-tailed?
Right.
Right-tailed. Okay, cool. Next, let's calculate the sample proportion. So that's P hat, which we know is the number of successes divided by the sample size, which in this case we were told at the random sample of 1,200 adult U.S. women, 504 self-identify as a crazy cat lady. So that's how we set up our fraction, correct? 504 out of the 1,200. Let's round to 3 decimal places. Oh, actually, it doesn't even go to 3 decimals. It should be exactly 0.42. Yeah. Okay, cool. Part C, calculate the standard error. So let me open up our notes here, or not our notes, our formula sheet. We are working with a single population proportion for this hypothesis test. Therefore, we're using our formulas from Unit 6. Okay, Unit 6 is when we're working with just a single population, as we're doing here. So from here, I go down to hypothesis testing, because that's where I'm working at, and I look at the standard error formula. It's given right here. Okay, this is the standard error formula, so this is the one we will be utilizing. Standard error equals the square root of p times 1 minus p all over n. Also represented as sigma sub p hat. So that's the square root of p times 1 minus p all over n. Where, again, be careful. This is where students, I think, make the most mistake. They'll accidentally substitute in p hat in here. But be careful. That's not what the formula says. The formula says p. So we use the p that you defined up here, and we said p is 0.4 or 0.40. Okay? So that's the square root of 0.40 times 1 minus 0.40 all over n. N is the sample size of 1,200. And I believe that should give you 0.014.
Yes.
Okay. Next, let's calculate the z-test statistic, or the z-score, which again, going to our formula sheet, we have that formula provided here. If you recall, in class, I gave you the option. I said you could also write it as z equals p hat minus p all over the standard error. So whichever format you prefer. I like to do it like this, but if you prefer this way better, it literally is the same thing, because mu sub p hat equals p as defined right here. So like this or like this. Up to you. But either way, oops, I want blue. Either way, the z-score equals, oh, it's still not the right color. What color was I using? This one? Okay, so the z-score equals p hat minus p all over sigma sub p hat, or the sample proportion, which we got was 0.42. Minus the population mean, which was 0.40 or 0.4, all over the standard error you just got on the previous step, which was 0.014. Plugging that into your calculators, going to 3 decimal places, that's 1.429. Yeah. Okay. Next page. find the p-value for your z-test statistic. So, to find the p-value, what function in our calculator do we use?
Normal CDF.
Normal CDF, good. So normal CDF, where the lower bound is what?
1.4.
The z-score, the 1.429, good. 1.429. The upper bound is then infinity because this was a right-tailed test, so we're going towards positive infinity. And then we always have 0 and 1. Going to 3 decimal places, I believe this gives you 0.077. Okay. Any questions up to here?
Quick question.
Yeah.
So for the standard error, I used p-cap for the values instead of p, but they're still giving me the same answer.
That is probably coincidence because 0.42 and 0.40 are fairly close. And when you divide such small numbers by a large, very large number of 1,200, it's probably a negligible difference. But if these weren't such close values, or if this wasn't such a large denominator, you'd probably definitely get more of a difference. So yeah, so ensure that you are using p here.
Okay. And then so now going to section E, when it's a two-tailed test, how do you know where to put the z-score?
Oh, good question. So, and we will do a two-tailed test today.
Okay.
Yeah, let's do it then. Yeah. Okay. So part F, do we reject or fail to reject the null hypothesis? Do we support or not support the alternative Y? I always like to start with the reasoning Y first. So we know our p-value is equal to, I'm going to convert this decimal to a percentage. So that's 7.7%. Is that less than or equal to your level of significance? Remind me, what was our level of significance?
10%.
10%. Where did I even say that? Oh, yeah, right here. 10% level of significance. So it is. Therefore, it is or is not statistically significant.
It is.
It is. So it is statistically significant. Therefore, do we reject or not reject the null?
Reject the null and support the alternative.
Good. Reject the null. And then similarly, support or not support alternative. We support alternative.
Professor,
Mm-hmm.
should we write the equation that way, or is it okay if we put p-value is less than the statistic?
Like you're using words? Words is fine as long as you do it out
Explain
fully.
it. Okay.
Like is less than or equal to the
Okay.
level, yeah. So next, state a conclusion in the context of the problem. So at 10% level of significance, the sample data supports the claim. And it supports because it was statistically significant. We said right here, it supports the alternative hypotheses. So it's going to support the claim. And then feel free to look back here to remind yourself what the claim was. Test the claim that at 10% level of significance, the population proportion of women who self-identify as a crazy cat lady is more than 40%. That's the claim. So we're now in support of that. So the claim that the population proportion, you just copy it on over, of women who self-identify as a crazy cat lady is more than 40%. Any other questions on this problem?
When you get like 7.7, did you just like take out the 0 from the p-value?
So good question. So the p-value is currently in decimal form. To convert to a percentage, you take the decimal, move it twice to the right.
Oh, okay.
And then unit 6, you said was like the independent variable?
So like,
Number 6 is a single population hypothesis test.
Yeah, like it's gonna be something that looks like that, and then you just move it over 2 decimal places, and that makes it 7%.
Any other questions? All right, what time is it? Let's check the time. Oh, we're doing good on time. Okay. So let's continue on to number 7. In a random sample of 5,230 all these questions are like cats and dogs. So just so in a random sample of 5,230 cat owners, 3,828 claim that their cat is indoor only. Like indoor only cats, right? You know what I mean? Okay. Using the sample data, construct a 99% confidence interval estimate of the true proportion of cat owners who has their cat be indoor pets or indoor only pets. There are parts A through F here, round all parts to 3 decimals if needed. I again want to give you guys a head start. I do not expect you to finish it in 5 minutes, but take 5 minutes to get a head start, see how far you could get.
So for the exam on a cheat sheet, can we, is it fine if we write that? one?
that I allowed that to be written.
Okay, okay. So we have it printed out in the email, so I just have a.
Yeah.
I'm still having trouble understanding how to interpret the confidence interval in the context of the problem.
So the question overall is asking the true proportion of cat owners who have their cats be indoor only. So this is basically telling us that the true population proportion of people who have their cats as indoor only will range between these 2 values as a percent.
Okay.
And then we try to be a little bit more specific because you need to include at what confidence level, but like that's the overall thought process.
Gotcha, thank you.
Because we don't know what the true population proportion is of how many people keep their cats as indoor only, but we at least narrowed it down to within this range.
Okay, thank you.
I just like answered it in one go instead of spelling it out.
how do you know conditions like?
Oh, I forgot.
Conditions
So
are-
we come to our formula sheet here.
Everyone sends
I'll just let you.
I don't remember what the estimated standard error is at the,
That's when you do n times p hat.
because it says that it's like this big fraction, but we have P1 and P2.
So you use p hat,
Comparing to my
But it's gonna
answer,
work.
We use P
or-
hat instead.
or just like-
because p wasn't given, so we use p
Well, what's
hat,
your
and that
N?
would be the, when you divide.
Then standard error, but then how does that relate to
And
the
is the
99%
sample size.
confidence error?
Because then once you get the margin of, once you get the estimated of error, we plug it in, and then we go to ZC, which was given in the beginning, and that's 99. So you use the 99.
It's the sample proportion. So, and that's what you just found here.
So like they're jumping ahead, but we have to like go
Okay.
back.
This is your sample proportion, so you take n, which is 52, and you multiply it by p hat, multiply it by standard error, and ensure it's greater than or equal to 10. And then
Oh, the
repeat
margin
here,
error, you're
plug in that
subtracting.
for n, 5230, and then n for p hat.
So it's P
Plug in the
minus E
Okay.
and P plus E. you'd have two answers.
No, yes, for B. I'm talking about C and D.
D.
About one more minute.
Hold on.
One more minute, we'll start going
I'm
over
sorry,
it.
I'm really bad at explaining.
This means multiply these, right?
Correct, has multiplication.
So this should be what D looks like. This should be the answer for D.
Following this, that's why I was really confused with. So following here, we were asking what is that normality of the, we just did standard, regular. And then we do that here. Then over here.
So I don't know if this is necessary
Margin
or
of
not.
error.
So when we're doing like interval notation, does this plus sign need to be included in the equation that we put in our calculator or not? 'Cause, I mean,
I
this
just
is.
needed something to reference.
Yeah, this isn't quite right.
No?
Almost. This is.
Cause remember we were asking, like, why does it say this? If it doesn't. have
Oh wait, this isn't the.
I have to wait then.
Okay, you'll see what we're supposed to be doing.
I might be.
And I think it'll make more sense then.
Yeah.
All right, guys. If you didn't finish, that is a-okay. But let's start going over it. Okay, so first off, we need to determine the sample proportion. So that's going to be p hat equals, so your number of successes divided by your sample size. So in this case, that's going to be the 3,828 divided by 5,230. Rounding to 3 decimal places, that is 0.732. Yep. Part B, are the conditions for approximate normality met? Again, feel free to reference your formula sheet. We are still dealing with a single population, therefore we're still using the Unit 6 side. We're talking about confidence intervals, so we'll look at our confidence interval. And right here, it says conditions for approximate normality. Conditions for approximate normality, you do n times p hat, you do n times 1 minus p hat, and verify they are both greater than or equal to 10.
For that, you could also base it off of if the successes and failures are greater than or equal to.
Correct. Yes, you could do that as well. So I'll go ahead and show both ways. So if you want to use the formulas, you do n times p hat, which would be 5230, that was the sample size, times p hat, you just found to be 0.732. And that will give you about, I rounded here to the nearest whole number, 3828. But I guess if I was doing this to decimals, let me just keep my decimal. Let me re-grab my calculator. 5230 times 0.732. If you were to do it this way, 3828.36. Okay. And then n times 1 minus p hat, that's 5230 times 1 minus 0.732. So 5230 times 1 minus 0.732, that'll be 1401.64. Which are both greater than or equal to 10. So are the normality criteria met? Yes. So that's one way you could do it. Another way you could do it if you wanted to, you don't have to, but another way you could do it is just identify your number of successes and failures. So successes is just the number of people who identified their cats as being indoor only. That was the 3828. Which is greater than or equal to 10. And then the failures, that's the total sample size, 5230, minus your successes, minus the 3828. So 5230 minus 3828, which is 1402. Which is also greater than or equal to 10. And as you can see, if I were to have rounded the first two I had done here, if I had rounded these to the nearest whole number, notice it's the same values you get here. So basically it's the same thing. It's just whichever way you prefer. So either way.
Professor?
Uh-huh.
Is part E supposed to be 99? Is that a typo from 95?
Yes.
Okay.
Yeah, good catch. Part C, calculate the estimated standard error. Okay, so estimated standard error, again, let's look to our formula sheet. We are still working within our confidence intervals, and it says right here, estimated standard error. It's given to us. Here is the formula. The estimated standard error is the square root of p hat times 1 minus p hat all over n. So that is what we will be utilizing. So the estimated standard error equals the square root of p hat times 1 minus p hat all over n. So compared to the problem before, in the previous problem, we used p. In this case, since we're talking about confidence intervals, we're using p hat. So please be careful there. So this is equal to the square root of p hat is 0.732 times 1 minus 0.732 all over n, which was 5230, which I believe should be 0.006. Okay. No, it's okay. No worries. Okay. Part D, find the margin of error. Again, go to your formula sheet. We are still working in confidence intervals. Find the margin of error. That is here. We are told the margin of error, E, equals Z sub C times the estimated standard error, where Z sub C, the critical value, you get from the table below. We are working with the 99% confidence, so we're going to be using this bottommost value. So 99%, this Z sub C is going to be 2.576 times the estimated standard error is what we just got in the previous problem. So the margin of error, E, equals Z sub C times the estimated standard error. Z sub C, we just said, was 2.576. That came from the table for a 99% confidence interval, times the estimated standard error we just got in the previous step as 0.006. Plugging out in your calculators, going to 3 decimal places, is 0.015. Yeah.
I have a question. Or part B, the second one, I put the whole thing that it showed me, so I put like 1401.64. Would that be wrong? See how you have it?
Oh yeah, no, yeah, that's totally fine.
Oh.
Yeah, yeah, either.
Okay, I was just looking at the right side.
Yeah, either of these is acceptable. Yeah.
Okay.
Okay. Part E, thank you for pointing out I had a typo on here. This should not be 95%. It should be 99%. We're doing 99% confidence interval. So write the 99% confidence interval in interval notation. Look back to your formula sheet. If you need a refresher, we are given it here. The confidence interval, we can write it in interval notation as p hat minus E, comma, p hat plus E. This is how we write our interval notation for our confidence interval. So we do p hat minus E, comma, p hat plus E. So in this case, p hat was, what was p hat? Oh, our p hat was at the top. That was 0.732. Minus E, we just got in the previous step, so minus 0.015. Comma, again, p hat, 0.732, plus E, the 0.015. Using your calculators, I believe this should be 0.717, comma, 0.747.
So we solve for it, not just write it.
I didn't realize you didn't, yeah.
Okay.
Yeah, exactly. You have to go one step further to figure out what that addition subtraction actually equals.
Can you show us how to put that into a calculator? calculating? That whole equation?
Oh, you don't do it all at once, you have to do them separately.
Oh, separately.
Yeah, so
Oh,
do
okay.
0.732 minus 0.015, figure out what that gives you, and then separately do the addition.
Okay.
Does that make sense?
Yes.
Okay. Part F, explain what the confidence interval means in the context of the problem. So we are 99% confident that the true proportion of cat owners, again, feel free to look back up here if you need to remind yourself what the heck you were even doing. Remember, we were trying to find the confidence interval to estimate the true proportion of cat owners who has their cat be indoor only pets, right? So that's what we just found. So I'm just retaking that, rewriting it down here. So we are 99% confident that the true proportion of cat owners who has, what did it say up here? Who has their cat be indoor only pets is between, and then you take your confidence interval and rewrite it in percentage form. So it's between 71.7% and 74.7%. So between 71.7 and 74.7% of cat owners has their cat be indoor only pets. And we are 99% confident with that. Yes.
Okay, so like what I plan to do, and I'm wondering if, cause like after I'm done doing, by the time I get through all these calculations and blah, 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 then I'm like, wait a minute, how do I word this again? So
Yeah.
like as soon as I get my exam, I go straight to this one, and as soon as I see the confidence, I see what it was my confidence level, and then I can write that intro sentence.
Yeah, if you want to, yeah.
That's what I
And then
like
just
to do.
fill in the number at the
Yeah.
end, yeah. I'm the same way. By the
Yeah.
by the time I get to the end, I'm like, what the hell was I even doing?
Yeah.
And so then that's why I even have to go back up here and I have to reread what our goal was. And then notice I just copied this word for word down here and just inputted the percentages. Yeah. Yeah, that's totally okay. Any other questions? All right, we got 3 more problems. Let's see if we could do them within this next hour here. All right, so number 8. Gallup conducted a national poll asking, do you have a cat? It found that more women than men have a cat for adults in the U.S. You want to know if a similar result holds for the city of Anaheim. You claim that the proportion of women who have a cat is more than the proportion of men who have a cat in Anaheim. You gather a random sample of 500 women and find 370 have a cat. You gather a random sample of 500 men and find 360 have a cat. Use the sample data and the steps below to test your claim at a 5% significance level. Let me first ask you guys something. Is this one population or 2?
2.
2. Good. All right. So, again, I'm going to set the timer for 5 minutes. I do not expect you to finish it in 5 minutes. Just see how far you can get.
We're doing women as our 1 and men as our 2.
Yeah, let's do women as population 1, men as population 2.
Can we just like keep that, do you anticipate that ever being flip-flopped? Like,
No.
I remember like women go first.
Just usually, if it doesn't really directly specify which population is which, it just goes in order. Whichever population came first, make that your population 1. In this case, women came first.
So that's our keyword right there. So then that would be greater than. Right?
Wait, for the no?
No, for your alternative.
Yeah, I think so.
I think it'll be good.
I think it's awkward.
So much. I think it's like the null.
If you wanted your women,
I don't know if
they
this is
sample
right.
the women's group.
Would it be like?
So like, you know how in the other
always
module,
being equal sign. Always.
Really?
For the null, yes.
Oh.
The only difference is that for two population proportion, automatically P1 equals P2. That's how you're starting, always. P1 equals P2 for the null for two population proportion. And then when it's a single population, like how we did here, it's still an equal sign, but since it's a single population, we're not saying it's another population. Rather, you just set it equal to whatever the percentage was that we're doing the comparison to. But it's always an equal
Makes a lot
sign.
more sense, okay, thank you.
Mhm.
Wait, so when you put equal sign, you have to put like a slash to it as well?
No, just equal.
Cause I remember like for a two-tailed test, it's like.
Yeah,
P
that's when it was
equals-
different from, but that would be in the alternative,
Mm.
not the alternative hypothesis, not the null. The null is always equal sign. Always.
So
always.
for this alternative, would it be, no, what this is asking greater than.
Yeah.
So it'd be P1 is greater.
Exactly.
And one and two are the same number, because you just like multiply that.
Yes.
Question, Professor? When it comes to the difference, we would be using this formula, cause it's saying the difference in the.
Correct.
Okay.
Yes.
Thank you.
So for this one, our null is still equal? Yeah.
Oh,
But
yeah,
our
and
null
null
is
is
equal.
You'll have one.
We don't just say P1 is equal to P2?
For your null, yeah, that's what you do.
Oh.
So is that, did I do that right?
Because this is, when you interpret this, it gives you this.
Professor,
But we want-
what is,
but
is
it's right.
calculate the difference in those third sample, it's the same thing as
Like up here,
asking for the
you will have
second
answered it up here.
Or-
Yeah, find the
74
sample proportions of each,
Mhm.
and then what is difference be?
Or whatever, like
Oh,
P1 is equal to
and
P.
times
I think they only.
Subtract.
Yeah.
Oh.
Difference means this.
Right?
So find,
I think.
find the
Okay,
sample
we'll see.
Oh,
portion
and
for the
then-
first one, find sample portion for the second, and then subtract this portion.
Oh, okay, wow. And is that only for two-tailed tests?
That's all, or two population
Or
proportions.
two proper tests? Okay. Okay.
I'm frustrated. Now I forget what next one, next two.
The successes.
Don't you remember that?
You don't have to go
Where?
This is the
Oh, yeah.
It's right, this like, isn't.
It doesn't.
Oh, I wrote it.
She said actual, like, example. So like.
Oh, we can write
It just gives
Yeah.
it down to you, on the day, I'll be like, okay, I went.
That's what she was asking, like, what
can she write?
I have
So I can
tests,
like make myself
I have
perfect.
tests and drives.
Okay.
I could do test all wrong the next day, you told me, what did I do wrong? I'm good.
It's under other section.
Yeah. What is P bar mean again? Forward proportion?
How are you guys doing? Do you want a little bit more time, or you want to start going a
Yeah,
little
a
more
little
time?
bit.
How about like 2 minutes? All right, 2 minutes. Yeah, we're doing okay on time, so we'll do 2 more minutes here.
0.73. So my answer is right. Your N1 and your N2 are these. So it's gonna be 500 plus 500, not 572.
So, I'm not supposed to be messing around.
There's no use for this. Like, I want to ask for this, you just do it and then you do it again. And then this part is gonna be, I feel like doing this just makes it easier to know which one is N1, N2, and successive division X's. But you don't need this.
All right, guys, let's start going over it. And it's okay if you didn't finish. So, part A. What is the null and alternative hypotheses? So, the null hypotheses, which is H sub naught. Since this is 2 population, automatically we know it's P1 equals P2. For the alternative hypotheses, or H sub A, we need to compare our P1 and P2. And in this case, it specifically says you claim that the proportion of women who have a cat is more than the proportion of men who have a cat in Anaheim. So that's going to be P1 is greater than P2. And it didn't ask for it. I forgot to include it, but is this a left-tailed, right-tailed, or two-tailed?
Right.
Right-tailed.
Even if it doesn't say it, should we put it just?
No, if it doesn't say it, then it's not required, but I want us to practice it in case it does say it. Part B, calculate the difference in observed sample proportions. So there's a couple things going on here. Difference means to subtract. What are we subtracting? The sample proportions. So first, we need to find the sample proportions. So, So P sub 1 hat. So for the women, let's see here. For the women, it was a random sample of 500 and 370 have a cat. So 370 out of 500. That is, I got 0.74.
Yes.
Okay. And then for the men was also out of 500 and 360 have a cat. So 360 out of 500. And that'll be 0.72. Now that we know the sample proportions, we can find their difference. Difference tells us to subtract. So P sub 1 hat minus P sub 2 hat. That'll be 0.74 minus 0.72, which is 0.02. Okay. Any questions? Okay. So next, let's calculate the pooled proportion. So tell me real quick, from the formula sheet, do I need to be looking at unit 6 or unit 7? Unit 7, good, because unit 7 is when we're dealing with 2 populations. And we're talking about hypotheses testing of 2 populations. Oh, and look, actually right here, could have used this on the previous example, but instead of P sub 1 and P sub 2, just be with hats. But what it's asking for right now is the pooled proportion. So here is the pooled proportion. P bar equals X sub 1 plus X sub 2 over N sub 1 plus N sub 2. So the pooled proportion equals X sub 1 plus X sub 2 over N sub 1 plus N sub 2. So we add together the individual successes. So that's 370 plus 360 over the individual sample sizes. For women, it was 500. For men, it was also 500. So this gives us 730 over 1,000, or 0.73. Next, let's calculate the standard error. Go back to our formula sheet. Standard error is given here. Standard error equals the square root of P bar times 1 minus P bar over N sub 1 plus P bar times 1 minus P bar over N sub 2. So the standard error equals the square root of p bar times 1 minus p bar over n sub 1 plus p bar times 1 minus p bar over n sub 2. So this is the square root of, so p bar we got in the previous problem as 0.73, so that's 0.73 times 1 minus 0.73 over n sub 1, so that was the sample size for the women. The sample size for the women was 500, plus p bar 0.73 times 1 minus 0.73 all over n sub 2, where n sub 2 is the sample size for the men. It's just coincidence that it was also 500. That should give us 0.028. Next, let's find the z-score. Let's go back to our formula sheet. The z-score is given to be here. Recall in class, I did tell you it was okay to rewrite it in the following manner. Remember I said, oops, we could do z equals p1 hat minus p2 hat all over the standard error. It's the same thing because this portion right here is exactly 0. Because we're starting off with the assumption that P1 equals P2 from the null hypothesis. But if they're the same, then that's just 0. So that's not even needed there at all. So then you could just simplify it to this format. And I am okay with you writing this on your formula sheet. So that's what we're using for our z-score. So z equals P1 hat minus P2 hat all over the standard error. We already got P1 hat minus P2 hat. We did that here. And we got 0.02. Over the standard error we just did in the previous problem, the 0.028. Rounding to 3 decimal places, I had gotten 0.714. Okay. So next we could find the p-value. So the p-value equals normal CDF. What's the lower bound? Good, the z-score, 0.714. And then the upper bound is infinity or 99999 because it's a right-tailed test, so it's going towards positive infinity. And then 0 and 1. So this will give us, I believe, 0.238.
Do we always like round before multiplying by 2?
You multiply by 2 if it was a two-tailed test, but this isn't a two-tailed test. So we leave it as is.
So I thought it was just like with yeah, never mind. Okay.
Yeah, the next example, we will see where we're multiplying by 2, but anytime it's a left-tailed or a right-tailed test, all you're doing is just the normal CDF. So state conclusions about the null and alternative hypotheses. Why? I like to start off with the why. So because our p-value is, converting this into percentage form, that's 23.8%. Is that, good morning, less than or equal to, I forget, what was our level significance? 5%. So is 23.8% less than or equal to 5%? No, it's not. So I'm going to put a red slash through this because that is not true. So our p-value is not less than or equal to our level of significance. Therefore, it is or is not statistically significant. Not. So it's not statistically significant. Therefore, do we reject or not reject the null? Not reject. Not reject the null. And do we support or not support the alternative? Not. Good. Not support alternative hypotheses. Excuse me. So now that we know in general what we're doing, we just retake this and state it in the context of the problem. So at 5% significance level, the sample data do not, again, not, right? Do not support the claim. And then feel free to look back to remind yourself what the claim was. I don't remember what the claim was. Let's go back and check. So it does not support the claim that, let's see here. Oh, right here. You claim that the proportion of women who have a cat is more than the proportion of men who have a cat in Anaheim. So it does not support the claim that the proportion of women who have a cat is more than the proportion of men who have a cat in Anaheim. I literally just took, I keep going to the wrong page. I literally just took the claim here. Proportion of women who have a cat is more than proportion of men who have a cat in Anaheim. I just recopied that and just at the start said we do not support the claim. We do not support the claim because it's not statistically significant, so we do not support the alternative hypotheses.
I have a question.
Yeah.
So for the p-value, do you want us to write 0.174 and then 99901? Do you want that?
I want to see your normal CDF written out. Yeah, I want to see what you're typing into your calculator.
Oh, because I was just gonna write the 0.2.
Just, oh yeah, great, good question. I want to see this, yeah.
And then Professor, if the answer was like a negative for the p-value, for the z-score, how would you input it for the normal CDF?
If it were a negative, more than likely this would have been a left-tailed test.
Okay.
So in which case it would be negative 99999
First.
and then the z-score, then
Okay.
0 and 1. Yeah.
Thank you.
Which I believe, for those of you who are watching the video, if you want to see an example like that, I believe we did an example like that in the bonus part A that we did
Okay.
last week.
Okay.
All right, guys, y'all are doing awesome. Let's continue. We got 2 more questions. Oh, yeah.
So if it, going back to G, if it is not statistically significant,
Uh-huh.
that means that, it is not
Then we do not,
reject the null and
Uh-huh.
not, so we reject it 3 times.
it's not that we're rejecting, it's just that we're making 3 statements saying that it's not statistically significant. We do not reject the null hypothesis. In other words, we're keeping the null hypothesis, and we're not supporting the alternative. Yeah. And did you get the packet?
No.
Oh, are there any more?
Yeah.
Okay.
Whatever happy name.
All right, guys, let's take a look at question number 9. A survey on pet ownership was given to U.S. adults in 2015 and in 2020. In 2015, 645 of the 1,022 randomly selected adults reported that vet care is too expensive. In 2020, 673 of the 1,140 randomly selected adults reported that vet care is too expensive. Test the claim that the proportion of U.S. adults who think vet care is too expensive in 2015 is different from the proportion of U.S. adults who think vet care is too expensive in 2020. Use a 10% significance level. All right, guys, I'm going to give you a 5-minute head start. You got this. 5 minutes.
Question, Professor. When it comes to rounding, but it's
Yeah.
okay. I'm like, it looks a little weird.
Oh, yeah.
Professor,
Mhm.
this one, because it's a two-tailed test, when we put in the p-value, I mean, the z-score, would that be the 999 first? Or you just continue to keep the z-score?
That's the one that it depends. So think about it for another minute
Because it's not equal, so I'm like,
because it depends upon the z-score
Okay.
for whether it's the negative 99999 that comes first or if it's the positive
Positive.
that comes second.
Okay.
Like, what if it's asking something else and it comes to something?
You're using proportion instead of difference.
How many of y'all want a little more time?
It's like a couple of minutes.
Like 2 minutes? All right, 2 more minutes, guys. 2 minutes. All right, guys, let's start going over it. So, all right, so what is the null and alternative hypotheses? So let's start with the null hypotheses. So what is the null hypotheses, guys? H sub naught.
P1 equals
Good. P1 equals P2. And then the I spelled that wrong. Alternative hypotheses, H sub A is what?
does not equal P2.
Good. P1 does not equal P2. This one's a little bit trickier. What was the key word to recognize that? Yeah, it's different. Where did that go?
Second to last.
Right there. Different from. So that's why we just wrote it like that. Again, it doesn't, I forgot to include that on here, but is this left-tailed, two-tailed, left-tailed, right-tailed, or two-tailed? Two-tailed, good. Because it's different from, it's a not equals. P1 does not equal P2 in our alternative. All right, so calculate the sample difference and observed sample proportions. So again, we need to calculate each sample proportion and then find their difference. So P1 hat equals, so we had two different timelines. We had 2015 and 2020. Let's do 2015 first. So in 2015, 645 of the 1,022. So 645 out of the 1,022 is 0.631.
Yes.
Yeah, okay. And then P2 hat, similarly for 2020. In 2020, 673 of the 1,140. So 673 out of the 1,140. And that's 0.59 actually. Okay. So then we can find the difference between these sample proportions. So that's P1 hat minus P2 hat, 0.631 minus 0.59, which is 0.041. Okay. Next, let's find the pooled proportion. Feel free to look to your formula sheet right here. Here's the pooled proportion formula. So we're just going to follow that. P bar equals x1 plus x2 over n1 plus n2. So that is, remember, x1 and x2 are the successes for those individual populations. Yeah.
So for our cheat sheet that we can use on the exam, for the pool proportions formula, instead of putting like x1, x2, can I just like make a side note where it's just like P1 plus P2? Because that's just the way I remember it.
But it's not P1 and P2. What I have allowed, what another student asked, is if it was okay to write successes for P1, successes for P2. That is okay. You could write that. But it needs to be, what you do include on it needs to be accurate. You know what I mean? So if you want to write successes for P1, successes for P2.
Okay, but like, is that like okay with you though if I just like make a side note on my own paper and you don't allow that?
I would correct it though if it's wrong.
Okay.
So if you just wrote P1, P2, that would be incorrect, and that would correct you on it. You know what I mean?
Sure.
Yeah. And I'll review it tomorrow also. Okay.
Yeah.
Oh,
well,
but
it's
he's
just-
writing something different.
She said like we can't write anything on the cheat sheet that we have when we use the exam.
There are things you can write that I will approve,
Yeah, like two equation things that
but what you write on it needs to be accurate. So if you write something on there that's not accurate, I'm gonna
It's like
point that
accurate.
out and say that that's not correct.
But it's like accurate for me then.
So you could write successes for P1, and successes for P2.
Okay, yeah, fair enough.
Okay. So the successes for the first population was 645, plus the successes for the second population was 673. The first sample size was the 1,022. The second sample size was 1,140. So this should be 1318 over 2162.
Yes.
Or in other words, once you round to 3 decimals, 0.610. Or 0.61. 0.61 is okay as well.
Like, we could get it. Yeah, me too, but yeah.
Next, let's calculate the standard error. Again, look to your formula sheet. our standard error is given here. All right, this is our standard error formula. So this is what I will be using. So the standard error equals the square root p bar times 1 minus p bar over n sub 1 plus p bar times 1 minus p bar over n sub 2. So we have the square root of 0.61 times 1 minus 0.61, because p bar, that's what we just got in the previous step. The first sample size was 1,022, plus 0.61 times 1 minus 0.61 over the second sample size, 1,140. In which I got 0.021.
Yes.
Yeah.
Okay. Any questions up to here?
So the 0 again is just like whatever,
Which 0?
because you put 6-1 and then it's 0.610.
Yeah, this is equivalent to 0.61.
Okay.
Yeah.
I'm just wondering.
Yeah, zeros at the end of a decimal are negligible if it's at the end of a decimal.
Okay.
Yeah. Because it's kind of like saying, you could think of it this way. Think of it like saying, $500.00 versus $500.
Oh.
Right? So kind of like that. Okay. Part M, find the z-score. We have the z-score formula here. Remember, you could use this one or this one. I prefer this one, so this is what I'll be using for the z-score. Z equals P1 hat minus P2 hat over the standard error. We already found P1 hat minus P2 hat. We did that here, which we got 0.041. Over the standard error we just did in the previous step, 0.021. So this rounds to 1.952. Okay. Time for the p-value.
I had trouble on this.
Yeah, this one's a little bit trickier. P-value equals, what do we need to include here since it is a two-tailed test? Times 2. Good. Since at the start we said it was a two-tailed test, you have to take your normal CDF and multiply it by 2. So 2 times normal CDF of, now here's the question, is it the negative 999 first followed by the z-score, or is it the z-score followed by positive 9999?
That was z-score.
Yeah, z-score first. And how do we know that? Because this is positive. Since our z-score is positive, the positive z-score comes first, followed by the positive 9999 towards positive infinity. Let's pretend for a second. Let's pretend that this were negative. If this were negative, then instead you'd be doing negative 9999 and then that negative z-score.
So it switches and then the 0 and the 1 it stays
Correct.
Stays the same?
Yes.
Okay.
Yeah. So since this was a positive z-score, you do that positive 1.952 towards positive infinity, 0 and 1. Okay. I'll just write it in red just for pretend, just so you have a reference. Okay, so pretend if the z-score were negative 1.952, right? Then how would that change here? Let's just pretend. Then the p-value would equal 2 times the normal CDF, but it would be negative 9999 first, and then the negative 1.952, 0 and 1. Okay, so just so you have it as a reference, we're just pretending that, but we're not actually doing it. Okay, so remember that 2 just comes over, okay? The 2 comes over. And I want you to find in your calculator what the normal CDF is, rounded to 3 decimal places. I had gotten 0.025. So normal CDF of 1.952, 99999, 0, and 1 is 0.025. Multiplying that by 2 is 0.05.
Now, can we just take it from the 2 times normal CDF blah, blah, blah to 0.05? If we put the 2 times?
Oh, like you already did in your calculator?
Yeah.
Technically, yes, you can do that. But for this exam and what we practiced in class is I want us to practice just doing the normal CDF first. That way for rounding, we're just all on the same page with regards to rounding.
I did it all first and then I times it by 2 and I got 0.051.
That's what I got.
Same.
Oh, did I mess up?
No,
It's just the one
I
man.
did it your way.
So mine, instead of
And
5%, I would have
Oh.
found 5.1%.
Oh, yeah. So that's what I mean. That's why I want us to just all of us just do it separate. That way we get the same result. It'll just be
Okay.
easier for me to grade.
Okay.
If I see a slight difference like that, I will check. And I'll be like, oh, did they just do it all in one go in their calculator? Oh, that's what they did. That's fine. Just for my end to make my life easier, just doing it in a separate step. Yeah.
Okay.
But you would still get it right.
So technically, like 0.051 is correct.
Yes.
Okay.
Yeah. I would still accept that, but just for us being here, I want us to practice just doing it separate,
Okay.
rounding first, and then multiplying by 2. Okay. Good questions. Any other? Yes.
Back to the p-value, if it's like a left tilt test
Mhm.
and it's a negative, a z-score, would we still do the negative 99?
Correct.
Okay.
Yeah. If it's a left
I
tail
don't know
test,
why I
it's
keep-
negative
okay.
999 and then the z score.
Okay.
Okay. So let's do our general conclusions. So what's our p-value percentage?
5%.
5%. What was our level of significance? 10. So is 5% less than or equal to 10%?
Yes.
Yes. So is it statistically significant?
Yes.
Whatever answer you get from that, then you multiply it times 2.
So we reject or not reject the null?
Reject.
Good. Reject the null. Support or not support alternative? And support alternative. Good. All right. Lastly, let's state our conclusion. So, at the 10% significance level, I can't spell level. Okay, let me redo that. Level. The sample data support the claim. And I need to look back to see what that claim was. The claim was, it says a claim that the proportion of U.S. adults who think that vet care is too expensive in 2015 is different from the proportion of U.S. adults who think vet care is too expensive in 2020. If you want to copy that claim word for word at this point, you can. I'm going to rephrase it just slightly, make it a little less wordy. So test the claim that the population proportion of U.S. adults who think vet care is too expensive in 2015 is different from that in 2020. Okay. Bye. Leave this here for another moment while you guys finish writing down. Let me know if you have any questions. Yes.
So my struggle is always the final conclusion.
Mm-hmm.
So,
Amen.
how do we know when it's, we're using a population proportion versus, just the sample proportion, like in our wording?
It's always the population proportion for our conclusions here. Because that's the goal. The goal is to determine, because, so like, let's look back to here, right? So the null and alternative hypotheses. So notice we're comparing population proportions. Here we're comparing population proportions. So all of this work we do below it is just to determine which of these is true, right? Or which do we reject or not reject the null? Do we support or not support the alternative? But it's all in reference to the population proportions. And then the work to determine that just utilizes sample proportions.
In number 8, we use the word sample data instead of population proportion.
So, and we use that here also. So we're saying that the sample, so that's what we worked with, right? Like our work was using the sample data, right? We used our sample data here, then we used our sample data values here, and then we kept using it throughout, right? Basically what we're saying is that the sample data we have will either support or not support the claim, but the claim is always with regards to the population proportion.
Because I feel like we kind of like dependent on the question, like on the beginning part,
Mm-hmm.
like what are null and.
No,
we
so
use
similar.
P versus P.
So similarly with number 8, again, we're dealing with populations proportions here. To make our determination, we use sample proportions, but our conclusion is just the sample data either supports or not support the claim. And the claim has to do with the population proportion every time.
Thank you.
Because that's the whole point. The whole point is that we don't know this about the population proportion, right? We don't know our conclusion about the population proportion. Because if we did, we wouldn't have to do all this work. So we need the sample data to determine our conclusion with regards to the population. Because we don't know what the population is. I hope that helps. Okay.
I'm just confused because, like, I don't know, I just always struggle with the wording.
Yeah, it takes practice. But notice how for these hypothesis testing, it always follows a similar pattern. We reference what our significance level was, okay? We say the sample data either supported or did not support the claim, and then we restated the claim. That's it. Say again?
How do I know if the sample data support the claim?
That comes from right here, from the previous part.
Oh.
So see, since we said it supports the alternative, it supports the claim. The claim is the alternative. Whereas in this example, notice how we said does not support alternative? Then it does not support the claim.
Okay.
So it definitely follows. Good questions, guys. Any other questions? All right, we got one more. I think we have just enough time for it. So a study asked participants to describe their level of concern that their pet would need vet care in the near future. Of 502 women, 104 responded that they were concerned that their pet would need vet care in the near future. Of 496 men, 85 responded that they were concerned that their pet would need vet care in the near future. Construct a 95% confidence interval to estimate the difference between the proportion of women and the proportion of men who are worried that their pet would need vet care soon. Let's say women are population 1, men are population 2. Okay? I'm going to set the timer for, just because of the time, I'm going to set the timer for 4 minutes. Okay, 4 minutes, and then we'll go over it together.
Professor, are you going to be able to stay
stay a little after.
Like, I have a question on the study guide. 'Cause
Okay.
The girls that on the table, we were a little confused on one of the interpretations.
Okay.
So I don't know if you could answer now.
I could try. I'll try to answer it real quick.
Okay.
I have a meeting upstairs.
Can
I could
just
try.
show you right now? 'Cause I understand this a little bit better than that. Let me see. Where's exam reviews? So when it comes to the p-value, are we always going to insert the p-value and then the difference, what we got, and then the null?
Okay, so the interpret the p-value, because you got the p-value to be, whoa, it was that small?
Yeah.
Wow, 0.003%. It's a possibility of observing difference in population. So, okay, so restate your question for me.
Is when we interpret the p-value, do we need to insert that material? Being what we got, which was
The
the
p-value.
p-value, and then the difference, and then what the assumption
So it's not
was.
always going to be the difference.
Oh,
It's only
okay.
the difference in this case because it's two population proportion.
Oh, okay.
Basically, what we're always going to say though is for sure under the assumption that the null hypothesis is true,
Okay.
there is a blank % probability of observing that we whatever value we
Okay.
got.
Okay.
Just depending
Because this
upon-
was like two populations. so it's a
Exactly, that's why
different
it was
response.
different. But if
Okay.
it wasn't, then it's just the sample proportion.
Yeah,
because we
it's
didn't take
smaller.
a difference.
Okay.
Sample proportions, yeah. But otherwise, yes.
And then another one was for these two, I guess, we were getting confused on the wording on what we're supposed to, like the confidence interval.
Based on the confidence interval, can we conclude that aspirin will reduce the number of heart attacks in adult males? So the confidence interval was negative 0.012 and negative 0.04.
So we're just like pulling the information we got and just.
So, okay, so with that problem in particular, I almost want to write this down. Okay, with this problem in particular, so we're comparing two populations. Population 1 was the males who took the aspirin. Population 2 were the males who had the placebo. Okay. Since our confidence interval is negative, that means when you subtract these two populations, this population of males who took the aspirin must have had less heart attacks than those who took the placebo. Because that's the only way to get negative results. If your first data value is smaller than the second, right?
Okay.
So that means those who took the aspirin must have had fewer heart attacks than those who took the placebo. Because, so for instance, let's say those who took heart attacks, let's say it was 5. Those who took aspirin, say they had 5 heart attacks. Those who took the placebo had 20 heart attacks. That's the only way to get negative, right?
Yeah, yeah.
Versus if it were positive, then yeah, we couldn't do that.
Okay, and that's when they said that. Okay, that makes sense. I guess it was just like understanding what the value.
Yeah, yeah. The fact that they're both negative means that P1 is smaller than your P2.
Okay.
So population 1 had less heart attacks than
That
population
makes
2.
sense. Okay.
Oh, and there was one more, right?
Yeah, it's group D.
Oh yeah, so same conclusion. Yeah, just I know the wording is weird,
Yeah.
but
Because it looked a little. Emma had mentioned like the homeworks didn't look too similar.
Yeah,
the
no,
wording is
don't-
a little, okay. But if we kind of get this.
yeah, as long as
okay.
yeah, you're good.
Okay.
All right, guys, let's start going over this. So, part A, find the sample proportions and the sample difference. So, we've done that a couple times now. We know we got to find each population's sample proportion and then subtract them. That's what difference means. Difference means to subtract them. So, P sub 1 hat, we're going to do the women first. Of 502 women, 104 said they were concerned their pet would need vet care in the near future. So that's 104 out of 502, which I got 0.207. Yeah? Okay. And then for the men, 85 out of 496 said they were concerned about needing vet care soon, which is 0.171. Yeah? Okay. So now finding the difference, P1 hat minus P2 hat, that is 0.207 minus 0.171, which gives us 0.036. Okay. Part B, find the estimated standard error. I'm going to go to my formula sheet. Again, I'm still on the Unit 7 side because I'm dealing with two populations here, but I'm not looking at the hypothesis testing because that's not what we're doing. We are in the confidence intervals, right? We're going to look at the confidence intervals. And within the confidence intervals, the estimated standard error is given by this formula here. P1 hat times 1 minus P1 hat over N1 plus P2 hat times 1 minus P2 hat over N2 and the square root of all of that. That's the estimated standard error for the confidence interval of two populations. So let me actually just see if I could copy that.
You're getting fancy with
I know, I
this.
love this. I'm just gonna keep practicing and keep practicing and
It took me a long time to actually know how. And then I see you, I'm like,
well, there many people are helping me with this, so.
I was hearing on whether I need a tablet, and I'm like, maybe I would.
It's just convenient with certain things. Okay, so P1 hat we found in part A, that was the 0.207. Over N1, the first sample size was 502. Plus P2 hat, we got 0.171. So times 1 minus 0.171. All over N2. N2 is the second sample size, 496. Okay, that was 0.171 times 1 minus 0.171. So here, this should give you 0.025. Yeah.
What's the correct way to abbreviate like estimated standard error?
You could just write it out or just do EST,
EST? Okay.
STER. Yeah, just kind of abbreviate it however you want. I don't have any particular preference. Okay. Next, find the margin of error. The margin of error is given down here, right? Here's the margin of error. Let me actually just do this margin of error. And again, recall that the Z sub C is dependent upon your confidence level. What's our confidence level? 95. So looking at our chart, 95%, that'll be 1.960. So we're using the table for that. Okay, so this equals Z sub C. Oops. Z sub C, we said 95%. That's right here, 1.960. Times the estimated standard error we did in the previous problem. That's 0.025. And that should give you 0.049. Okay. Part D. Write the 95% confidence interval in interval notation. So let's look back to here. Interval notation is this guy, confidence interval. And this is the interval notation. P1 hat minus P2 hat minus E, comma, P1 hat minus P2 hat plus E. Okay, so similar to when it was one population, but slightly different because we're dealing with two. We already know what P1 hat minus P2 hat is, right? This portion right here, we already did. We did that here. So you're just taking this value, subtracting E, then adding E. So it's 0.036 minus E you got in the previous step, 0.049, comma, 0.036 plus E. So you get negative 0.013, comma, positive 0.085. Okay. Lastly, let's interpret it in the context of the problem. So we are 95% confident. Confident of what? Look back to the problem if you need to. Construct a 95% confidence interval to estimate the difference between the proportion of women and the proportion of men who are worried their pet would need vet care soon. That's what we're doing. We're looking for the difference between the proportion of women and proportion of men. So I'm just going to take that and restate it. So we're 95% confident that the difference between the proportion of women and proportion of men who are worried their pet, who are worried their pet would need vet care soon, is between negative, I'm going to convert these to percentages, negative 1.3% and 8.5%. Now you might be like, what the heck? How is it negative? Well, it's a difference. Basically, you're subtracting those two populations, right? And when you're subtracting values, you could get a negative. So what we're saying is that either, so let me just write, you do not have to write this out. I'm about to do in red. So what we're saying is P1 minus P2, where remember, P1 was the women who were concerned and P2 is the men are concerned, right? So if it's negative, that means the amount of women is less than, or population proportion for the women is less than the population proportion for the men. Basically, women are less worried than men. That's how you would end up with a negative. Or you end up with a positive, being that the women are more concerned than the men. So you could have it either way. Technically, it could even be 0, because 0 is in between those values, right? But at least we have a more narrowed region within we're looking to determine what their difference is. All right, guys. Woo, that was it. Let me stop this recording.